So on behalf of Meyer Sound and my fellow colleagues, welcome to another MAPP 3D Roundtable. The spirit of these roundtables is that we would like to make ourselves available to ask any questions that you might have relating to MAPP 3D. As always, on these calls, I'm being joined by fellow panelists, not necessarily all of them, but typically there's at least 3 of us. It's my understanding. I saw Steve, I heard Steve already, so Steve is with us. Alex is with us. I think David Vincent is with us. We have some Latin American colleagues in here as well. Today, we're going to talk about connection to the Compass control software as well as Compass Go. For those that are not familiar with those applications, we have dedicated webinars, which can be found on our YouTube channel called Thinking Sound. Dedicated webinars talking about Compass as well as Compass Go. Those webinars and many more, including previous roundtables, can be found on Thinking Sound, our YouTube channel. As always, we make a point out of it of informing you that the primary support is still the dedicated MAPP 3D help website. This is your first line of defense, and it has tons of valuable information. Great time and effort was spent in creating that page. It has animated graphics, it has video clips and whatnot showing you all the routine procedures and much, much more. So if you're new to MAPP 3D, be sure to visit that page. If you go to help from within the MAPP 3D application, help in your main menu bar, then help will also directly take you to this website. And that means that we can look at today's topics. Today's topics will be how to interpret the delta dB metric, which is new in MAPP 3D, didn't exist in MAPP XT. So we need to talk about that. And then how do I connect to my Galaxy devices and Compass control software and Compass Go? We're going to do that not using an actual Galaxy. We're going to use a virtual Galaxy, but for all intents and purposes, that is exactly the same approach. And that means that the first thing that we're going to look at is how to interpret the delta dB value in MAPP 3D. Whenever you have a microphone living in your design and you go to the measurement view tab in the center pane, which consists of your frequency response, or let's say virtual sim, well, then there's also the headroom portion, which shows you all Spl metrics, A-weighted, C-weighted, and Z-weighted, as in zero weighting, as in no weighting. But you might have also noticed that to the right of that bar chart, that spectrum, there is a column showing you your loudspeakers. And in that table, there's a column which is called delta dB. And we need to investigate what that means. What does the delta dB mean whenever I drop in a microphone into my design and start looking at these Spl metrics? What does delta dB mean, and how does it relate to my generator level, which at this time is still living in the top right corner, but in today's version of MAPP, it's living in a top left corner, and that's something that not yet fixed in the keynote presentation. So we're going to talk about our generator level, and we're going to talk about the delta dB value. First, let's talk about the generator level. When our generator is set to 0 in MAPP 3D, you can think of it as the following. Think of your sim machine, which has a potentiometer on the front panel. We can also set that potentiometer to 0 or to its calibrated position. And whenever you do that and turn on the generator, then you're producing pink noise, provided you chose pink noise as your excitation signal. And the average level of that pink noise signal, expressed in volts RMS, will be 0 dBV, which is 0 dB more with respect to 1 volt, ergo 1 volt. So out of your sim machine, when the generator is set to 0, you got 1 volt on average, 1 volt RMS of pink noise coming out of your sim machine, out of your generator running at 0 dBV. And that means that if we are to feed that signal to a Galaxy without bells and whistles, so all input gains as well as output gains are still a unity, then the Galaxy is essentially the best next thing to a copper wire. So we're feeding our 0 dBV of pink noise into our Galaxy device, and that means that without bells and whistles, what is coming out of the Galaxy device will be 0 dBV of pink noise. And if we feed that signal to our loudspeaker, then we will read a certain level, depending on where our microphone lives, at what distance our microphone lives to that particular loudspeaker within my MAPP 3D model view. And within MAP3D, that gives you several metrics. There's your average A-weighted value in the first column, or I should say third column. And then there's your average C-weighted value, your average Z-weighted value, and then there's the Linear Peak Spl. And linear in this context means that there is no onset of either compression or distortion. So input and output of the loudspeaker still follow each other perfectly in lockstep. And that's the value that we see under Linear Peak Spl. But you might also notice that in the column next to it, there's something new, which is referred to as max Linear Peak Spl. And those numbers are not the same. In fact, if you look carefully at the numbers, you will see that there's an offset, a delta of 5.2 decibels between the linear peak when the generator runs at 0 and a value which, for whatever reason, is substantially higher, the max linear peak, which from what it appears lives 5.2 decibels above my current linear peak. So it looks like there are some decibels being left on the table that we can utilize. So why don't we start with a second iteration? We're going to take our sim machine. We're going to send the same signal to our Galaxy, but this time around, somewhere within my Galaxy device, which I could do at several stages, it could be input gain, I could do it in the matrix, I could do it on the output gains, but somewhere within our Galaxy, we're going to elevate the signal by 5.2 decibels, which means that out of our Galaxy suddenly is no longer 0 dBV coming, suddenly there's plus 5.2 dBV coming out of that Galaxy. And that means that the input voltage that is now being presented to our loudspeaker is 5.2 decibels hotter than it was before. And now I've completely utilized those remaining 5.2 decibels. And now we have achieved the max linear peak Spl value. It is at this point that the scales start to tip. If we exceed this value, then we enter the domain where the loudspeaker will no longer be running in its linear range of operation. Then we will start to see the onset of compression and or distortion. But up to this point, the loudspeaker is perfectly within its linear range. If you would like to know more about the stop conditions that we use to determine the max Spl of a loudspeaker, be sure to visit mnoise.org, where we have a written procedure that explains in great detail which stop conditions we use to determine the maximum level of a loudspeaker in such a way that it's still ensured that it's within its linear range of operation. That delta dB basically shows you the remaining amount of headroom that you can utilize between 0 dBV and, depending on make and model, the ultimate level, the max linear peak Spl that you can attain. And that is in a nutshell what the delta dB value means. So for a single enclosure, that delta dB value is always the difference between the linear peak at your current generator level and the maximum attainable peak value if you increase that level, in this case by 5.2 decibels, which can be done in several links within the signal chain. I could also increase the generator level to plus 5.2, and then I would utilize that same remaining headroom. So there's several links within our signal chain where we can increase, in this case, the level by 5.2 decibels and utilize that remaining delta dB, that remaining headroom. And for a single enclosure, you can rely on that data as it's shown onto your screen. Let's see then how this works once we start working with more than one loudspeaker. The thing with maximum linear peak is that in the calculation of that value, time and therefore phase is discarded. And while it's true that 10 loudspeakers give you the potential to gain as much as 20 decibels in a team effort, this will only be true if you are equidistant to each loudspeaker within that array. And that would mean that you would have to deploy the arrays you're seeing in this illustration, which would be concave or convex. I always mix those up. If you live at the origin of this circle, then you're equidistant at the same radial distance to all of those loudspeakers. And equidistant, of course, translates into equitemporal. So in this instance, which is the exception and not the rule, you would expect to see a 20 dB performance increase if you go from a single loudspeaker to 10 loudspeakers. But we all know that this is not how you deploy arrays. If anything, then they're concave rather than convex. And that means that if we deploy arrays the way they are intended to, it gets a little bit more convoluted. Let's look at a MENA array. And the reason that I'm using a MENA array is solely for educational purposes, because the MENA array is the last loudspeaker of a generation where a single element would have a flat response. I don't like flat because flat is open to interpretation. You could have a single slope and you would find people that would call it flat. So I prefer equal amplitude. As in, if I have 1 volt at 100 hertz, then in a flat response, it is expected to produce the same amount of SPL as the same 1 volt at 1 kilohertz or the same 1 volt at 10 kilohertz. I think equal amplitude is less subject to interpretation. So here in MAPP 3D, we see our 4 viewports with 4 distinct camera angles. We have our 3-dimensional isometric in the top left corner. Then we have our plan view or top view in the top right corner. We have our section view in the bottom right corner, and we have our transsectional view in the top left corner. This is an array of 10 elements, and in theory, one could argue, well, if we go from a single enclosure to 10 enclosures, we could potentially gain as much as 20 decibels. We can already sense that this is not going to happen because we're not meeting those conditions that you saw on the previous slide. So let's capture the performance of a single enclosure first. So on axis to loudspeaker 5 from the top, indicated by the cross, we have a microphone, and we're going to first look at the contribution of that single element at that distance. So here we see a prediction at 8 kilohertz. We're only going to look at the contribution of that loudspeaker on its own. Notice that on the right-hand side that I've already utilized my delta dB, whatever the value might be for a MENA enclosure that differs per make and model, but the delta dB value reads 0, and that means that I've already utilized whatever remaining headroom there was. I've already utilized that to the best of my abilities, as you can see in the top right corner. Now let's look at the Spl metrics for that single enclosure. In the active trace, we see our average SPL 0 weighted, which means no A weighting, no C weighting, 0 weighted average value. It reads 19.3 decibels. And the linear peak value at the distance where our microphone lives reads 12.5 decibels more, because MAPP 3D uses pink noise as the excitation signal, and pink noise has a crest factor, a peak to average ratio of round about 4. And if you really want to split hairs, then in a Meyer sound ecosystem, that translates into 12.5 decibels. So that linear peak SPL value is living 12.5 decibels above the average value. However, in the last column, we see the potential performance boost that we can attain in the team effort, which is 10 MENA elements at once. And that's about 20 decibels more, allegedly. Not almost, it's 19 decibels. It's 1 dB shy of the theoretical maximum. But that has to do with the fact that where that microphone is living, you're not equidistant to every enclosure into the array. And that means that even though time and therefore phase might be discarded, that you still have your inverse square law, your attenuation loss over distance. You still have that introducing minute level differences, because the loudspeakers that live at the edges of the array had to travel a longer distance to that same microphone, and therefore are attenuated slightly more with respect to number 5, loudspeaker 5 from the top, that is staring directly in the microphone membrane of our measurement microphone. So we have minute level differences. And there's, of course, also the angular attenuation. These loudspeakers are not omnidirectional. They might be omnidirectional at low frequencies, but line array elements exhibit a behavior known as proportional Q, which means that as you go up in frequency, that the coverage angle starts to narrow proportionally. So you have angular attenuation, you have coverage behavior, if you will, dispersion, and you have distance that introduce minute level discrepancies. And that is the reason why we're not seeing a 20 dB increase, but it's pretty darn close. So we have the promise of gaining 90 decibels. Whether we get to utilize those 19 decibels in a team effort, that remains to be seen. Because now we're not going to capture the response of a single element. Now, for the first time, we're going to look at all MENAs at once. We're going to compare the data that we now see for the entire array, and we're going to compare that and see whether this promise of 19 decibels of alleged gain in a team effort, if we get to utilize that 90 dB. Again, I've maxed out all delta dBs, and the first thing that you might notice is that there's a change in the spectral content, because suddenly we see this huge buildup of low frequencies, which is the mutual team effort at low frequencies, where we're in the joint custody of all those low frequency sections. So that's perfectly normal behavior, and that means that whatever increase we see in level is primarily caused by the mutual coupling at low frequencies. But now let's look at the actual Spl metrics now that we're measuring the entire array at once. So in the second row from the top, we have stored the performance of that single MENA element on its own, soloed. And in the active trace, the live trace, now we see the metric for all MENAs turned on at once. And let's look at the differences. Notice that when we had a single MENA element, that it produced a peak value of 102.8. And again, with 10 elements, we're expecting to see a 19 dB increase in efficiency. And this is also true when we look at the numbers for all MENAs at once. But if we look at the difference in linear peak at the point in space where a microphone lives, then we see that we only gain 17 decibels, which is 2 decibels shy of what was promised. So we don't get that max linear peak Spl, we get 2 dB less, as you can see. And that means that, especially when you're working with multiple loudspeakers, that if you need a level for your particular production, for your particular application, if it exceeds the max linear peak Spl, it's not going to happen. You can think of the max linear peak Spl as the ultimate result, and the linear peak Spl, provided you utilize your delta dB, your remaining headroom, as the penultimate result. And that's what we're seeing. The penultimate result differs by 2 decibels from the ultimate result. And that 70 dB increase is primarily due to the mutual coupling at low frequencies, because we're looking at zero-weighted data. If we ignore the low frequencies altogether by using an A-weighting curve, which is essentially a high-pass filter, then we see that the increase in level is even less than the 19 decibels that were promised, let alone the 17 decibels that we see when we have no weighting curve applied. Because if we look at the A-weighted values, where we're basically looking at the frequency span in the custody of the waveguides, then we see that we're only gaining about 14 decibels if we ignore the mutual coupling at low frequencies. So rather than seeing a 10-fold increase in pressure, we only see about half of that. We only see a 14 dB increase rather than a 17 dB increase, let alone a 19 dB increase. So for a single loudspeaker, you can take that delta dB value at face value. With multiple loudspeakers, that maximum linear peak Spl value is just an indicator of the maximum level that you could attain, but only if all the stars and all the planets are aligned. That's in reality, it's not going to happen. So the metric that you want to pay attention to is your linear peak Spl, which is your penultimate result. This is by no means an easy topic, but the nice thing about delta dB is that it really allows you to adjust all the gain settings within your entire system to make the most out of your system, to get the maximum amount of efficiency without leaving any decibels on the table. Then the next topic that I would like to discuss is connection to Galaxy. What we are expected to see over here is the processor settings tab in the center pane within MAPP 3D. So we have our model view, we have our object settings, and then we have our processor settings. Okay, so we have our processor settings. I'm going to share my screen once more. So that is all MAPP 3D. At the same time, I have Compass running. And in Compass, we have a single Galaxy. It's an 816. And for all intents and purposes, this could be an actual Galaxy, but I'm going to use it virtual. And then in the top right corner, we see a screen capture of my iPad, which is currently running Compass Go. So several things are going to happen. If we're going to use the Galaxy in our mature Compass control software, then we expect it to appear on Compass Go, because Compass Go is saying, hey, I see a galaxy on the network. So I'm going to my iPad, I'm going to connect to that virtual galaxy. There we see the overview tab in Compass Go. I don't want to go there, let's go to one of the output channels. And let's go also to output channel 1 in the Compass control software. So we're seeing those outputs. And now I go to MAPP3D and I go to that same output channel, and I'm going to do several things which are probably extremely ill-advised, but they're only here to serve a purpose. Think of it as the following, okay? You're doing your design within MAPP3D, and you're also doing all the processing that you're expecting to do in the real world. You're using your delay integration, your product integration, your EQ starting points. You might be using LMBC, low mid beam control, and whatnot. All of that has been done in MAPP3D, and now I want to somehow get that out of MAPP3D into the real world, into my Galaxy devices. So here's what we're going to do. We go to our MAPP3D, and then we go to Tools. And in Tools, we go to Signal Processor Management, and that will bring up a dialog. And on the left, we see our Galaxy device that is living within my MAPP3D world. I think I can make this even a little bit more obvious by changing the name to, let's call this the MAPP3D Galaxy, okay? If we now go to our signal processor management, we see this is the galaxy living in my MAPP3D ecosystem. But on the network, we have a galaxy living, which is called My Galaxy, which is a physical galaxy. We're using virtual one, but for all intents and purposes, that is the same. So that is the one living on the network. That's the one living on the network. So we're going to say in MAPP3D, select discovered device. And that will bring up a dialog, and it says, I see a galaxy which is running in virtual mode. Let's choose that galaxy. And now we have the option to connect to that device from the one in MAPP3D to the one on the network. And we can do that in two ways. We can push all the settings that we made in MAPP3D, and we can push those to the galaxy living on the network. Or if you like to do your settings, your delay integration, product integration, low mid beam control, all of that within Compass Go, or you have projects that you simply wish to recall because you've already done all of that, you can also recall that project in the mature Compass control software and then pull it from Compass into MAPP3D. So you can do it either way. This time I'm going to push from MAPP3D to the control software, and when I hit connect, boom, everything updates instantaneously. So I'm done. At this point, we're synchronized. We're talking to each other. This is full duplex communication. We're talking to each other, and that will remain from here on. So let's close this dialog. From now on, everything is synchronized. There's no master, there's no satellite. Everything is now becoming bidirectional communication in near real time, which means that if I go to my all-pass filter in MAPP3D and start to change the corner frequency, then you see that change of the corner frequency of the all-pass filter reflected in near real time in the Compass control software, as well as in the Compass Go software running on my iPad. If I disable my U-shaping, then everything updates in near real time. It also works the other way around. So if I were to go to my high-pass filter and start changing the corner frequency of that high-pass filter, then everything is updating in near real time. And this is also true if I were to go to my iPad. If I were to change any of these settings within my iPad, such as the corner frequency of that same high-pass filter, then everything updates in near real time. So whatever you do from here on, they're synchronized, and they will remain synchronized for the remainder of this session. And that is wonderful. That means that you can do, you're on the bus or you're in transit, you can do all of your design work in MAPP3D and then push it in a single effort to your Galaxy processor on the network. Or you could do your design work in MAPP3D and do all of your programming, all of your settings and whatnot in Compass Control, if that has your preference, and then pull it into MAPP3D. And the other thing that I think is quite awesome is that you can also use MAPP3D to document your work during the event. So imagine that you designed a system, you made your settings, and for whatever reason, once the event is over, you're not entirely happy with the results. Well, if I store that map3D session, then all the settings that I made, all the changes that I made during the events will be captured. And that means that if I'm on the bus or in transit to the next production, I can review my work and start thinking about what I might want to change for tomorrow's show. So it's also a great way of documenting your work, your tuning, your toning, and at the same time using your Compass Go, to walk the venue and tone the system, voice the system to your liking. And all of that is now being documented and there for you to review and incrementally improve your production, improve your application. So that pretty much concludes the how do I connect to Compass, how do I connect to Compass Go. That concludes the official part, the things that we wanted to show you, the delta dB value, as well as the how do I connect to the Compass control software and how do I connect to Compass Go. So all of that is talking to each other in near real time. And that means, unless my fellow panelists have anything to add at this point, that we get to go to the Q&A. Can you talk more about what it means when the delta dB is a positive value? Yeah, I can. So over here, I've got a loudspeaker. The horn is rotated in such a fashion that it is 80 degrees horizontal and 50 degrees vertical. We have a microphone living at 4 meters distance to the loudspeaker, to the front of the loudspeaker, that is, to where the loudspeaker grill lives in space. And if we go to the measurement view, then we see that with the generator set to 0, in the top left corner, with the generator set to 0 for pink noise, we see a positive value. You're exceeding the maximum input voltage with pink noise, mind you, that you can feed to this loudspeaker before you see the onset of non-linear behavior. So the takeaway from this is that if I were to feed 0 dBV worth of pink noise to this loudspeaker, that we're already going into the domain where the loudspeaker is becoming nonlinear, which doesn't meet our standards. So there are several ways that I can appreciate this. I can attenuate my signal generator by negative 0.25 decibels, in which case that value now reads 0. So I've lowered my generator, quite literally the potentiometer on the front panel of my sim machine, I've lowered it by 2.5 dB, and now we're back at 0. So this would be the ultimate drive level, the maximum input voltage for pink noise that we can feed this UPJ1P. So we lowered our generator level by 2.5 decibels, and now we have 0 decibels of delta dB of headroom left over. And let's store this, okay? I'm gonna store this trace, and let's call this generator at negative 2.5 decibels, okay? And let's take note of the Linear Peak Spl. Now, notice that Linear Peak Spl and the Max Linear Peak Spl are the same number, because the Max Linear Peak Spl shows you the number that you can attain when you utilize your delta dB value, which we did. So now they're one and the same. That gets us 110.3 decibels. I'm just going to save that. Now that lives in the second row of my stored traces, because now I'm going to add back those 2.5 decibels, which means that we exceed the maximum linear peak. And if I do that, what you will see is that my values do not increase. So, I mean, this is a little bit of a over-exaggerated scenario, because this would indicate brick wall limiting. But what you see, and in the real world, it's not, it's not a compression ratio of 1,000,000 to 1. But what you would expect to see if you go into the nonlinear domain, that you would see that the system is no longer linear, and that output and input no longer follow each other in lockstep. You would expect to see compression. You would expect to see, for every dB that you increase your input level, your drive level, you would expect to see less than 1 dB of output because you're nonlinear. But if you now look at those values, if I highlight those using attenuation, then you see that with the extra 2.5 decibels, which you do not get to utilize, that you see no increase in linear peak, which is a bit of a severe example, but that is the spirit of the data that we're showing you, which is that you're exceeding the maximum attainable level. So you can drive and drive and drive more, but your system is going into compression, so you will not see a proportional increase in output. Now, if we were to go in the other direction, so if we go back to the if we were to go back to the previous scenario where we lowered our generator by 2.5 decibels, okay, right on the money, we see the same values once more. If I now were to lower this by another 10 decibels, now you see your linear peak value, you see a drop. You can see that in both cases, the max linear peak is still the same, because that shows you the ultimate result when you utilize that delta to B value. But our linear peak values are now different by 10 decibels. And that is also being reflected within the delta to B column. It's now saying, okay, when you run the generator at this level, you're leaving 10 decibels on the table. So in this case, I'm tweaking the generator level. But of course, I could also do this very same thing by zeroing this out once more, in which case we're 2 dB over. But this time around, I could go to my processor, and rather than lowering the generator, I'm going to lower the processor output by 2.5 decibels, in which case I get the same result. Because as I said during the keynote, there are several links in your signal chain where you can increase or you can lower the level at your discretion. I was noticing that with the UPJs specifically, why do the UPJs behave this way? Are the UPJs expecting a signal lower than 1 volt? But what you're looking is at different sensitivities. And Steve is also with us. Steve, correct me if I'm wrong, but we're looking at different sensitivities.
That's true. And if I've got it right, the input sensitivities were scaled against other models of loudspeakers that were currently in production. So the UPJ was scaled against the M series, the Milo, the Mica, the Melody.
Right. So there needs to be some historical awareness that when the UPJ was made, that it was a companion loudspeaker for Mica, Milo, and whatnot. Whereas with today's Ultra X40s and Ultra X20s, these are companion loudspeakers that are intended to be mated with lions, leopards, and linas and whatnot. So there's also some historical context to this, but I'm more than happy to stand corrected.
And we do have the input sensitivities listed on each speaker's data sheet.
Okay.
Hi, I have a question.
Sure.
So once I imported the drafting, can I rotate? Like I wanted to change the X and Y axis like 90 degrees. That's possible after I imported the drafting, or I should re-import it?
Alex, it's
so I would respond that there are no tools to edit DXFs or SketchUps once they are imported. So the best thing you could do is to edit that in that AutoCAD or SketchUp software and then re-import that drawing, because there's, like I said, no way to edit an imported drawing. So yeah, that's mainly something you need to do before bringing it into MAPP. So you can always re-import and just just discard the old one.
Okay, thanks so much. And another one is, can we create some object so that it's going to represent real, like a pillow or mezzanine level, so that we can see the prediction of shadow or those kind of stuff in the MAPP 3D. I haven't tried it yet, but.
Like acoustic shadows, like occultation?
Yes, sir.
That's not possible at this point.
Okay.
That being said, Hidenori, keep submitting those feature requests, because those feature requests will help us prioritize the development of MAPP 3D.
Yeah, great. Thanks so much. I just wanted to. Thank you.
Thank you.
I'm going to mention something in regards to Hide's question that can help him. If you let's say you have a balcony and you have an under balcony area, you can turn on the center lines of the speakers and make the prediction surface so that it does not go through, and then you can see that the speaker gets blocked and does not reach under the balcony. So it doesn't show you acoustically, but you can see where you have sightline blockage. And I use that all the time. I think it's a really powerful feature. We didn't have that available in MAPP XT. You just had to go through and kill yourself to get that information. So you can see in 3D if you have a path from a speaker to a seat.
So let's see if,
show an example of that?
yeah, I'm cooking it up as we speak. So we have a prediction plane. If you go to the bottom right corner, then you see that my loudspeaker is actually living above the prediction plane. So I'm going to select that loudspeaker. I go to my express settings, and simply using my up and down keys, I can now tilt that loudspeaker. Now, at this point, if I hit that prediction plane, then the center line is protruding out of that prediction plane on the other side. So let me see if I can make that more visual. So we have this center line, it hits my prediction plane, and then it comes out at the other side. Now, in reality, there's no such thing as acoustically transparent concrete. So one way that we can make you appreciate this is by going to the properties of that particular surface and deactivate the true option. And the moment that I do that, that center line is no longer capable of penetrating that surface and coming out on the other end. So now, if I'm not hitting that surface, then my laser continues indefinitely. But if I do hit that surface, then it stops. Unless, I go over on the other side. Now I'm not hitting it, and now it's, going on. It's merry, on its happy journey. So by purposely deactivating the true option, you get to do a, let's say, a optical line of sound verification or validation.
Great, thank you for showing me.
Yeah.
Thank you.
I would just mention that whenever I have when I'm doing any predictions on a room that has more than one level, I always turn off all the through function so that everything is so that you get the full blockage.
I see. Yeah, great. Thank you. Thank you, Bob.
Derek Murray is inquiring, what is the maximum ground plane dimension possible? Is it limited by 100 by 100 meters? And then fellow Meyer Sound colleague David Vincent replied that the maximum is 1 kilometer, which would be about 1,000 meters and roughly 3,000 feet. Let's go to Lucas. Lucas, it's all yours.
Yeah. Hi. A couple of things related to using the center lines to know, if you're hitting a balcony or not. That's very good, but sometimes you hit them sort of in a diagonal angle and you're not really sure. Like using the center lines, it's not, you don't really know if you're hitting it from the side. So it will be maybe useful to have some sort of lateral center line, or like a dispersion cone or a coverage cone, something related to that, or beam width maybe. Like having, actually sort of a projection or of a cone or something like that. To know if you're hitting the sides. But my question was actually related to the delta dB. Does it take into account equalization?
If I understand correctly, then your question was, if I apply any processing, will that affect the delta dB value, the headroom that is available to me? Well, in reality, it does. But that behavior at this point, correct me if I'm wrong, that behavior is not yet reflected in MAP3D.
That is accurate. I think the linear peak that is measured of these loudspeakers is a broadband measurement, and I don't believe we're taking into account if you were to, high pass it at the crossover, how much you'd get extra or less. So I think it's just a broadband linear peak measurement that we're working around.
That was exactly the question. Thanks.
If we apply a boost, then we're likely to expedite the onset of nonlinear behavior. Whereas if we, apply a cut or start, reducing bandwidth, then it's the other way around. It's likely that some decibels might be left over on the table, but that behavior is currently not reflected in MAP3D. No.
If you think about real headroom for real loudspeakers, it really is a frequency by frequency basis. Like let's take a little speaker where it overloads at 60 hertz is very different from where it overloads at 600 hertz and where it overloads at 6 kilohertz in terms of SPL numbers. So it's a complicated subject. A defective speaker could have a single range that craps out before any other frequency. I mean, that's what what you get when you go to the music store. And in professional audio, we make sure our systems overload very nearly at the, across the range very similarly and in an expected way. But when you start and you put a filter in, you're entering into that area, especially like Merlijn says, a peak filter. You're making somebody hit his overload ahead of everybody else. It's a very long subject. It would require so much processing power to anticipate the headroom capability of every frequency. A lot of leftover processing power will set on that.
Yeah, and this is something that became even more apparent when we started developing M-Noise. It's a little bit off topic, but it's not just, how do I process it? It's also greatly depends on the program material. So, interesting side effect is that M-Noise and ping noise below 500 hertz are functionally the same. So in certain loudspeakers, you will see the onset of compression occur at the same drive level, regardless whether I use M noise or ping noise. So for whatever reason, the bottleneck is in the low frequency section. But with the development of M noise, which has a crest factor as a function of frequency, we suddenly started noticing that there are loudspeakers that with M noise no longer start to go into compression in the low frequencies first, but suddenly, because of the different excitation signals, start to go into compression at high frequencies first. So as Bob rightfully so pointed out, it's a very, very involved topic. That being said, if it has your interest, then definitely be sure to visit mnoise.org, where there's a treasure trove of information. Okay, so at this point, we still have one more roundtable scheduled, which is going to be the roundtable next Thursday, September 24th, 9 a.m. Pacific time, 6 p.m. Central European time. So on behalf of Meyer Sound, myself and my fellow panelists, much appreciated again. So thank you for watching, and please stay safe. Please remain healthy, and best to you and your loved ones. And see you next week, hopefully. Bye-bye.